Hello everyone, I hope you're doing well. So in today's video, we're going to go through the 2025 VCE Northern Hemisphere Maths Methods Exam 2, the extended response questions. I hope this video finds you well and helps you with your method studies. I just want to say congratulations to the students that did it 2 days ago, the Northern Hemisphere papers. I hope it went well. I know a lot of you struggled with the exam one, and I totally agree. It was something that was it was ugly a little bit. The multiple choice section, I did the multiple choice section for exam 2, and it was really nice. Now, this is my first time trying the actual extended response, so I'm going to give my rating afterwards, like after I do this paper, and hopefully it's good. I hope, it was not too bad for everyone. But yeah, this is my first time trying it out. Again, these are suggested solutions, so VCA hasn't posted the solutions. It probably takes 2 months to actually upload them. They take so long. So if you see any mistakes, please let me know, yeah? I am a human. I'll easily make sometimes mistakes, yeah? And just like always, guys, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And let's smash through this video. Actually, before we smash through this video, I just want to say a disclaimer. I will take very long doing this paper, and there's a reason why, because I want to explain the concepts, the basic concepts. For those students who really struggle with the basic concepts, this video is going to be very long, and it's going to be really good in terms of getting the basic concepts, how to break down questions, how to critically think for those hard questions, and how I'm going to break them, yeah? So it's good to watch those. I'm going to show you my thinking process, and hopefully it helps you develop those critical thinking skills. So let's go through this paper. So question 1. Consider the function g, where it has a domain of all reals, and g of x is this function. Find the x value of the stationary point of inflection of the graph of g of x. Now, of course, the most obvious is, to find the derivative and let it equal to 0 and blah, blah, solve. Now, you can do that, but it's quite obvious what you can see. This here, it's actually easy to draw. The function, like you can see the function, g of x isn't actually hard to draw. If you know how to, graph polynomials, we know, like for example, x squared minus 1, we can write it as, of course, difference of perfect squares, so x minus 1, x plus 1. And then you're left out with x plus 1 here, squared. Which, these come together, it's basically x plus 1 to the power of 3. Now, if you graph this is a positive polynomial, as you can see. And we have x values at, so we have x values at -1 here. So imagine that's -1 here. And we have at 1. Okay, perfect. So the graph is actually going to pass nicely through the point 1. But when it approaches -1, because it's cubed, it's actually going to have this point of inflection. It's going to look like that. It's one of the most ugliest graphs I've ever drawn, but yeah, like that. Like that. Actually, that looks like that. So draw like a point of inflection like that. You see how there's a point of inflection at -1? So your actual point of inflection is at -1, just by inspection, yeah? So, for example, find the value, means there's only one value. It's at x equals -1. That should be your answer. Now, you can also let's define this using our CAS, so that's your answer. Let's also do this by CAS, of course. How do you do it by CAS? Let's go on our CAS, and of course, define it. So g of x is going to be, x squared minus 1 times x plus 1 squared. Now, well, the most obvious in this case, what you can do is graph it. Just, go in a graph, g of x here, graph, and you can see that this is a minimum turning point, but we want a stationary point of inflection, and we can see it's over here. So we can just go menu, we can go to analyze graph, and we can go to inflection point. There it is, -1, 0. But we only want the x value, so it's -1. Of course, you can also do it by algebra. So, for example, you can derive it. So, yeah, derive it. Let it equal to 0, because it is a stationary point. We solve answer from x. And so these are your x values. Remember, this x equals half is your minimum turning point. This here is your x value for your point of inflection. So x equals -1 is our final answer. Beautiful. Next question. Find the coordinates of the local minimum of the graph of g of x. It's only 1 mark, so we've actually just done that in our paper, didn't we? Haven't we just done that? So we learned, remember, so when we derived it, yeah, we found that the stationary points are x equals -1, which we know that's a stationary point of inflection, and this is x equals half, which is as our local minimum turning point, yeah? So our x value is a half. But what about our y value? Because remember, we're talking about coordinates. So to find that, it's basically just subbing it back to the original equation. So g of a half. So your y value is negative 27 over 16. So let's write that quadrant down. It's only 1 mark, so just do over your CAS quickly. So that's going to be nicely written. So basically half, let me write that nicely. Half, comma, negative 27 over 16. That is the answer for this one. Whoopsie. All right. Let me highlight that. So 1 mark, just make sure you put the answer, nothing else, no extra working out. Next question. Find the average rate of change of g of x between x equals 0 and x equals 2. Very, very easy question. So you remember to find the average rate of change. So it's going to be, for example, in this case, your average rate of change. So I'm going to say rate average. So 8, just put a little bit average here. You don't need to write that, but I'm just explaining what the formula is. It's going to be g of 2, so g of 2 minus g of 0 all over, 2 minus 0, which is, in this case, 2. So this is the formula for your average rate of change. So, which is, just put it in your CAS because it's 1 mark. Straight away, let's do that. So go in your CAS, put the division. So g of 2 minus g of 0. Oopsie, that's not equal. So minus g of 0 over 2. Press enter, and this is your average rate of change. It is 14. So let's write that down. 14. Now, to be honest, it's 1 mark, so straight away, you don't need this extra working out. I just show the extra working out for a lot of students to understand where I got the answer, but it's just x equals, so your average rate of change is just 14. Next question. Find the equations, there's many equations, of the tangent lines to the graph of y equals g of x that have a gradient of negative 2. This is easy. Well, we know that to find the gradient of a tangent at any point, we derive d dash of x, yeah? So when we derive g of x, this gives us the gradient at any point, so x, the gradient of the tangent, yeah? But we want our gradients of our tangents to have a gradient of negative 2. So we want to equate this to negative 2. Does that make sense? So find the equation of tangent lines to the graph of y equals g of x that have a gradient of negative 2. And so what we can do is we can go on our CAS and actually solve this equation for our x values, which x values have a gradient of negative 2, and we can easily find the equations of the tangents from that. So let's go to our, basically our, CAS. And so what we're going to do is we will derive g of x, yep, and we will of course equate it to negative 2, and we're going to solve this answer, comma x. So these are our x values where the gradient is negative 2. Let's write that down. So x equals negative 3 over 2, and x equals 0. So, of course, to find the equation of the tangent, you can just do it with a CAS. So let's do it with a CAS. Remember, to find the equation of a tangent, all we can just do is go to menu, and we go to calculus tangent line, where we write the function, so g of x, comma x, and at what point do we find the tangent? We have to find two tangents, so let's find the first one. So you sub in this x value, put it right there, enter. So this is your equation of your first tangent. The same with the other one. Take this over here, and just replace the x value with 0. And this is your two equations of a tangent, where you can see that the gradients of these tangents, so negative 2x, is negative 2. I hope that makes sense. Beautiful. Let's write those down, those two equations. So we can say, I'm going to call it y1. So the first tangent, for example, is just negative 2x minus 43 over 16. y2 equals negative 2x minus 1. Okay, that's nice. Beautiful. So we found the equations of the two tangents. Beautiful. Is there any mistakes? That looks quite good. Yeah, so d dash of a, so for 2 marks, yep, we've found the x values, done. Next question. Describe a sequence of two transformations that maps. Whenever you hear the word maps, just kind of, I always replace it in my head. Maps is the same as transforms. So imagine, describe a sequence of two transformations that transforms the graph of g of x to the graph of this, which is, as you can see, that there's two transformations that's happened. And you can, by inspection, we can already see what's happened. First of all, they have, as you can see, they have reflected it. So, right, like you say, reflection. They have so it's a reflection along the, so we can say along the y-axis. This is a reflection along the y-axis. And what does that do? Remember in functional notation, so if you have g of x, a reflection in the along the y-axis, if you reflect it in the y-axis, it will become g of negative x. Yeah? Make sense? So that's what's happened here. Make sense? So that's where we get that. Can you say that negative x there? That's a reflection along the y-axis. And then you can actually see that there's a translation to the right. So like to find the translation, all you can do is just basically solve the inside. So what's 1 minus x equals 0? X equals 1. It means it's been translated 1 unit to the right. And then what's happened is a translation 1 unit to the right. That's it. That is really easy. And we can actually use all of these here to kind of understand it. So for example, we know like the way you can also double check your answers is, for example, we know that say you have f of x here, yeah? And let's call it equals to g of x, yeah? For example, f of x is your f of x, yeah? If we reflect, if we do a reflection in the y-axis, it will become f of negative x. We sub in the negative x inside here. So it'll be g of negative x. You do the same here. And so imagine this, replace that again with f of x. Imagine just call that f of x again, yeah? But this is the first part. Look, that's the tick. Look, we have that negative x. And then the next one is translation 1 unit to right. You would write that as f x minus 1. So imagine subbing that into that x. So it'll be negative x minus 1. That will be, simplifying it, it'll be negative x plus 1, and which is the same as you can see, 1 minus x. You can write that as g 1 minus x. Same thing, basically, if you're wondering. So we can 100% testify that it is correct. These are your two transformations. It's really easy, believe me. Don't overthink them. Really nice if you know your basic transformations. Translation 1 unit to the right. That is your first page. Not too bad. Okay, next question. Let a and b be positive real numbers such that the graph of y equals a times g of x plus b has a local minimum on the x-axis. Let's think what's happened here. So first of all, let's go really deep analysis here. First of all, they've multiplied the original function g of x by a, this by the way is called a dilation by a factor of a parallel to that y-axis. So let's write that down and I'll explain everything. So just to develop, so dilation. So what they've done is the dilation by a factor of a parallel to the y-axis. And what they've also done is that they've translated b, because a and b are actually positive. So that's if a is also negative, then there's a reflection, but there's no reflection. It's just positive, and b is also positive, means it's been translated up units. So, and we can say that's the first thing, and then the translation, we can say there's a translation b units up. We can say up. There's no because it's positive, it's going to be translated so that's what's happened here. Well, let's go back to our original graph. You remember when we drew this graph here? Let's take this graph over here. Let's go bring it down here and use it to help us do this question here. Let's make it larger. Okay, so for example, what we want is we want the minimum, the local minimum on the x-axis, yeah? Can you see this is your local minimum over here? Now, what was our local minimum? Our local minimum in our case was half negative 27 over 16. Isn't that correct? So that's our local minimum. Okay, now what we've basically done here is all these transformations that we've done don't actually affect the x value. Let me explain. So if you had two coordinates, yeah, x and y, yeah, two coordinates x and y, a dilation. So the first one, a dilation by a factor of a parallel to the y-axis. It means basically all the y values are getting multiplied by a. So only the y values, so it'll be x, a, y. You can also write this a dilation by a factor of a from the x-axis, the same thing, but I like to write it parallel because it's more easy to understand. Do you see what's happened? So this here, first one, has multiplied, basically all the y values get multiplied by a. So for example, what's going to happen here? This here, you're actually going to have an a in front of your, you're going to have an a in front of the y value for your minimum. Isn't that correct? Remember, it doesn't affect the x value, yeah? because it's parallel to the y-axis, all the y values get multiplied by a. So imagine we've done that. So the y value for our minimum turning point is already multiplied by a. Okay, perfect. And then at translation b units up, is plus b. So it only, affects the y values. When you're translating something up, it only affects the y values, and they all get translated up. So for example, nothing happens to our x value. Imagine this one here, u plus b. You see that? That's what's happened here. Understand that? So that's what's happened. Let's write it down. So basically, so imagine we've done this. So for example, let's take this here, and let's just reproduce it here. Let's reproduce it here. Let me put it here. Now, what's happened is, what we're doing basically now is, can I move this up? Yeah, I can. Okay, so what's going to happen is, like, for example, it's here. What I want to do is, I want to dilate it by a factor of some parallel to the y-axis, and then translate it some unit up. We want it to be around here. Look, can you see here? We want it to be that the minimum turning point is on the x-axis. Now, if you think about it, yeah, we've done all these transformations. Look, we've done all these transformations, yeah? But what is the y value that we want it to be the end? So remember, look, the x values doesn't change. So it's still a half. But for it to be in the to be the minimum point on the x-axis, the y value has to be 0, yeah? Because it's going to be on the x-axis. So imagine that we've done all these transformations. Look, all these transformations over here. So let's write that down. So on the, it only affects the y value. So like we've done, for example, negative 27 over 16, basically times a, plus b. And we want all of these transformations to result in the overall y value to be equal to 0. That's what we want. So, in our question, it says, express b in terms of a, just basically make b the subject. So it'll be b is equal to 27, actually a, over 16. That is your actual b in terms of, a. So we can, it's only 1 mark, so you can actually rub all this out. But I really wanted to explain it really in detail what's happening, yeah? Why these transformations are happening. So we can write that right over there. Okay. Now, so what I'm going to do is, we can also kind of double check it, can we? For example, let's go on our graph, yeah? What I'm going to do is to kind of do this. What I'm going to do is do this. I'm going to copy this. I'm going to make a new problem so it doesn't affect my other values. And I'm going to go here and, for example, I'm going to repaste that, yeah? Now I'm going to make a new function. Let's call it f of x. And I'm going to express it in terms of what's happened. So it was a times g of x, yep, plus b, yeah? That's your new function. And I can actually graph f of x, yeah? I can graph f of x, yep. Look, a and b, I can play with a and b. Now remember, a and b are positive values, they told us, yeah? So I'm going to put 0 here, the value is 0. Now let's think about it. You know how when we got our, this expression, yeah? So we when we did all our working out, we found out that b has to be equal to 27 a over 16. Isn't that correct, yeah? It has to, fit this. For example, let's say a equals 1. Look, when a equals 1, so if a equals 1 here, what does our b value have to be equal? It has to be equal to 27 over 16. So look, when a equals 1, what does our b have to be equal to? 27 over 16. So we can copy that there, enter. Can you see how our minimum turning point is at, the x-axis there? And it works for all of this. It's like a general solution, think about it. So for example, what about a equals 2? Or like, I don't know, 30, because it's positive, yeah? If you do that, it still works. So like, for example, when a equals 30, let's put 30 here. And then your b value has to be this here. Enter. Do you see how it's still on the x-axis? So this is a general solution. That's how it works. I hope that makes sense, yeah? Let's go back to our paper, and yeah, that is perfect. So b equals 27a over 16. I hope that makes sense. Next question. I'm going to put that back here. Just this one here. Okay, next question. For each real number x, let g of k be a function where now g of k is this, so it has a domain of all reals. Okay, so it's basically similar to the other function. Find all values. So there's many values of k for which the graph of y equals gk of x has exactly one x-intercept. Okay, not too bad. So to find the x-intercept of a function, we of course let gk, so let gk of x be equal to 0. Isn't that correct? And we solve it, don't we? So imagine doing that here. So of course you can see a difference is a perfect square. So imagine factorizing it. So x minus root k, x plus root k, x plus k all squared equals 0. So your solutions are going to be x equals root k, x equals negative root k, and x equals negative k. So these are your x, intercepts, yeah? But what values of k, what values can we have where we exactly have one x-intercept? So one only exists. Let's think about them. Let's play around here, understand what's happening. For example, let's sub in 1, yeah? If I subbed in 1, like for example, if I subbed in k equals 1 as a question, yeah? K equals 1. If I subbed in 1, what will, this will be 1. This here will be negative 1. And this here will be, again, negative 1. Can you see how these two are the same? So basically they make one solution, but you also have this different one, x equals 1. These give us two solutions. No, this doesn't work, yeah? It actually doesn't work. What about 2? What about 2? Let's try 2 then. Or, 2. 2, same thing, like root 2. Negative root 2. So these are already totally different. Doesn't even work. It actually doesn't work. You see that? What about 3? What about 4? What about 5? What about 6? All these positive values are not going to work because, say for example, 100. You have 100, but this is negative. It's going to be negative 100. So these are already going to. So any positive values is not going to help us in getting one exact solution. But what about 0? Think about 0. So for example, if you put 0, which is one of the most easiest way to think about it, if you already put 0 in here, so if you put k equals 0, look how beautiful this becomes. Because you can even by inspection look at it. If you let k equal 0, x here will be 0, x here will be 0, and x here will be 0. Can you see how all of these solutions are the same, x equals 0? They make up one x-intercept. So k equals 0 is a solution. It actually works. It gives exactly that one intercept. Of course, it says values. There's many more. And there is, because you need to think about them. Okay. We know that we have two square roots here. Isn't that correct? Now, we know a square root does not exist if the inside of it is negative. Isn't that correct? So if I put negative value, like for example, k equals negative 1, yeah? Think about it. If k equals negative 1, this won't exist because it will be square root of negative 1, doesn't exist. Yep. This also won't exist because it will be negative root negative 1, doesn't exist. But it will exist for this one. It will be positive 1 because, negative times negative 1. Beautiful. I think you're learning. You can see the pattern here. So when you have negative x values, these all don't work, these two. This one actually works. And this one's only going to always give us one solution, one x-intercept. Does that make sense? And it works for negative 2, negative 3, all negative values. Like, does that make sense? So if you had, negative 5, yeah? So it'll be, again, you can't put negative k equals negative 5 because if you do that, this doesn't exist, this doesn't exist, this exists. It'll be x equal. As you can see, I think we can see the pattern here. Basically, your k values, your k can basically take negative infinity, so all the negative value till 0. Remember, till 0, and 0 can be included. Because remember, when we included 0, it worked. Like when we included 0, didn't we? Whereas when we, put positive numbers, it didn't work. As we saw, we put 1, we put 2, we put 3, we put infinitely going positive. You're not going to get anywhere because it's always going to give you those two solutions. So absolutely, that looks perfect. Now, let's double check it. We cannot just assume. The way I always double check my answers is by actually just graphing it. Let's do that. So let's actually look at this and graph it. Maybe it's wrong. Maybe it doesn't work. So we gotta be careful. Sometimes graphing is so important. A lot of people think mistaken that. Not even graphing is, yeah. So for example, let's go to, okay, we haven't even defined g of k. All right. So let's rub this out. Okay, let's call this g of k, of course, where this is k, of course, and this here is k. Beautiful. So this is g of k, and let's, graph it. G k of x, yeah? So g k of x, enter, and we have k. Now we said, look, k equals 1. As you can see, it has two intercepts, but look, and remember every positive value. Look at the positive values. Look, as we go positive, 3 intercept, 1, 2, 3. 1, 2, 3 still. Look at that. It's just going to be infinitely. Like, the more you go to the positive, there's always going to be 3 x-intercepts. But when we reach 1, you can see that there's only 2. But which is problem. We only want 1, remember? But when you reach 0, it becomes like x to the power 4, yeah? Does that make sense? Because, you know, this becomes 0, this becomes 0, it'll be this is x squared and this is x squared, then multiply, it's x to the power 4, which is just a minimum turning point that crosses 0. So this is only one x-intercept, but look, in negative values, guys, negative values, look at that. 1, 1, 1. Look, it just goes infinitely. Just, you can go to, like, I can't write negative 100 because then I have to zoom it out and stuff. But let's say, like, negative 20. And yeah, like, you know, go menu and, you know, zoom fit it. But you can see, look, if you go on the left, it only crosses at once. So any negative value, so it's all okay. It's all negative infinity to 0. It's where 0 is included. So that's my answer for that one. Beautiful. Let's go to the next question. Find the values, so there's many values of k, for which the graph of gk of x has exactly one stationary point. Okay, so how do we do this? Let's just do this with our CAS, and then we can take everything that we do in the CAS and put it in our paper. So let's go back to our CAS, yeah? Now, so I'm going to actually just take this here and go back to my original and define it here. Okay, so we know that to find any stationary points, how do we do it? Well, of course, we have to derive it. So derive it, so gk of x, and we have to let it, the derivative equal 0. And of course, we solve for x. And here it is. So we got one stationary point, another stationary point, and another stationary. We have 3 stationary points. Remember, we want exactly one stationary point, yeah? So we need to think about it. By the way, as you can realize, these k values, because k can be any real number, yeah? This is going to give you everything. This is, like, this one here is, because any k values, this is already going to give you one stationary point. This is a problem. This one here already, like, if you put k equals 1, negative, blah, 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 it already is a stationary point. Guess what we have to do? We have to be smart. It means if this is already, like, going to be a stationary point, we need to make these two to not exist. Because remember, we want one stationary point. But how do we make them not exist? It's not bad, believe me. Because remember, you can see a square root here. If you see a square root here, to make it not exist, we make what's inside. Remember how inside of a square root, it cannot be negative? We can take the inside, because they both have the same inside. We can take this here, which is the inside of the square root, and make it to be less than. Less than means negative of 0. And we can solve that, answer, comma, k. And here we have a beautiful k values. It's saying k values are between negative 8 and 0, where both are not included. Now, be careful again. Double check your answers. Do not just assume. So, how do we double check our answers? Let's go back to our slider, our initial slider, yeah? So let's write, what is it? Negative 8 to 0. Okay. Okay, I need to, come on. It's ugly. Why is it like 1? What about if I put, like, for example, if I put 1, because I want to look at it back to the original graph. Zoom fit, please do not zoom. Can I not nicely zoom it? It's not work. Like, I want it to be like what it was initially. Do I have to, like? Yeah, it's rubbish, bro. Like, come on. Okay, what I'm gonna do is, let me just regraph it then. There it is. Look, let's regraph it. GK of x, and now, look, whatever I do to this, it will affect this one. Okay, this one's better. So why can I not put that slider there? Can I not copy and paste the slider, by the way? No, can I not take this? Yeah, I don't know how to do this, but who cares? So for example, let's, you remember we put it in this domain, yeah? You see this domain here? Forget about this one. We're looking at this one. Yep. Okay. For example, we said that. Look, can you see? For example, yeah, this is a pain. Let me just control end this whole thing and redefine the question again. Because yeah, I don't want to confuse myself. G of x, of course, is going to be x squared minus k times x plus k squared. Okay. So what I'm going to do is, of course, go back to where I was. So gk of x. So gk of x, and we have a slider. Okay, so as you can see. Now, we said negative 8 to 0. So negative 8 to 0. Let's double check those. And where they're not included. So as you can see that we only have one stationary point. As you can see here. This is perfect. This is what we wanted, didn't we? Yeah? We just need to double check if that works for all. Look, one stationary point, one stationary point, one stationary point, one stationary point. What about, like, okay, what about this? Because you know how they said 0 was not included. What about if we put 0? But, yeah, remember k equals 0? If you put 0, it'll be x to the power 4. Which, also has one stationary point. Why did it say 0 was not included? That's wrong. So 0 is actually also included, guys, yeah? Make sure 0 is also included. Be careful. See, sometimes you cannot just assume. So, okay, so 0 is included. What about 8, though? Look, what about 8? Let's put -8 here. Can't see here. Can I zoom fit it? Please don't tell me it's gonna mess it around. Yeah, it's messed it around. Okay, that's a pain in the ass. But okay, what I'm gonna just basically do is you can just inspect it. So we know, for example, when we derive, of course, gk of x and equals 0, and we solve answer comma x. These are going to give us a stationary point. For example, can you see when I put -k equals -8, what does it give me? When k equals -8 and I'm trying to find the stationary point, it already gives me 2 stationary points. That's a problem. Remember we wanted 1 stationary point, yeah? So k -8 doesn't exist. So do not include k equals -8, yeah? I don't know why this graph is really rubbish, but yeah, k equals -8, just by, deriving it and subbing k equals -8, it doesn't work. It gives you actually 2 stationary points. What about 0? Remember going back to 0? Redoing this whole thing. So solve answer comma x. You see, just 1 stationary point. What about the other values where you remember they were between, like -4, let's say? So same thing. Solve answer comma x. Look, just 1 stationary point. And this is what I mean. Like, what about -7.2? So those values in between actually do work. So, and I think solve, basically solve answer comma x. Look, yeah, they're always giving you so perfect. So basically from what I've seen, gk of x, it won't, let me redefine it. I'm sorry, but I think we've got the answer right now. But I do want to absolutely be 100%, is it sure? And because we also need to show some working out, and I'm going to show you what I would write. Because I've done some, okay, x plus k squared. Okay, there it is. There it is. And we said it was -8 and 0. Okay, there it is. As you can see, yeah, this is perfect. Look, for example, when it's at 0, minimum turning point. Look, that's perfect. Look, turning point is 1, 1, 1, 1, 1, 1, 1. And when you reach -8, we said that it's, when it's at -8, it has 2, didn't it? Now, I can't see that -2 though. Like, I can't see it, but it is likely to be somewhere there because it said x equals, yeah, this gives you, be careful, -8 is not included because we checked it also there. Now, how do you get full marks? To be honest, this is what you do. You basically go back to your CAS, yeah? Go back to your CAS. I'm just going to control and everything. And do this. Like, this is what I'll show you in my working out. Like, what we just did with our CAS. For example, what we did was we first, let me redefine it. I don't know why I've been redefining this equation for so long now. It's actually really annoying. Because, when you, x plus k squared. Okay, for example, you know how we, we said we derive it? That's what you need to first show. We need to show that we have to derive it and let it equal to 0, yeah? And write this down. And then we solve it, answer comma x, and we solve for the values of x. So you want to write all of these down, yeah? Then what you want to show is that this square root inside here, we want to solve it when it's less than 0. Yeah, like that. You remember? And when we solve it, we get, for k, we get -8 less than k less than 0. But we can say that 0 is included. Yeah? Beautiful. And -8 is included. No, not included, and we just write our answer. So it will be basically our real answer is this. Okay, so 0 is included, but -8 is not included. Why is it? Yeah, that's -8. Yeah, beautiful. Let's write what we are going to write. So let's go back on our paper. That was a little bit big lot talking, but yeah, but that's how you do this one. So, for example, what we'd say is g dash of k of x is equal to, from looking at it, it's 2, x plus k, 2x squared plus kx minus k equals 0. Easy? And so, of course, we want g k of x equals 0, which gives us x equals, looking at my thing, it's square root of k plus 8 minus k over 4, and x equals negative square root. So expanding that, k plus a minus k over 4, and x equals negative k from what we said. Now, of course, for example, if we subbed in, k equals, also 0, we said 0 here, 0, 0, yeah, it's 0, absolutely gave us, that was perfect. And so we've got all of those here, yeah? Now, what we want to do is we know that k, the inside the square root, we take it and we solve it when it's less than 0, which gave us that k is between, going back to the thing, k is between 0 and negative 8. But we know that 0, like when k equals 0, it gives us one turning point, one stationary point. Stationary point. So your final answer, we can write, your overall final answer, you can say k is an element from negative infinity, what negative infinity? Negative 8, sorry. Negative 8, where, negative, it's not included, to 0 included. Remember, 0 is included. Be careful. Do not mistaken that. That is one of the, that's why it's 3 marks. There's something wrong with it. It's mentally, it's not normal. And that's how I would approach that question. Once we're there, that's it. That's all you need, to be honest. Is there anything that we are mistaken? That looks perfect. It doesn't look too bad. Yeah, it looks good. Okay. Next question. Question 2. Consider the function f, which has a domain of D, where f of x is this, where D is the maximal domain of f. Find the domain. So we want to basically find the maximal domain. Now, this is very easy because you can just write it in your CAS and your CAS can find you that maximal domain. So let's first do that by CAS, and we can also try doing it by hand. There's many ways, but of course do it by CAS. It's so much quicker, but we'll also talk about how can you also find it by hand. So what we're going to do is we're just going to basically, let's control end this whole thing. We do not want that anymore. And we want to go to calculator and we want to write, f of x, and we want to define that function. F of x is for E3 log E, so 3 log ex. Okay, so of course to find the domain, you write domain of f of x comma x. This is your domain, basically 0 to infinity, where 0 is not included. Make sense? So let's write that down. So your domain is just x as an element, 0 to infinity. Okay, that is your domain. That's it. You just straight away get that mark. Now, because you only need that. But how would it, it's also good to know how can we get it. Say we didn't actually, the CAS doesn't, is not giving us the answer. And how do you actually do it by hand though? So it's important to note, okay, we're looking at this function, yeah? There's it's like a function inside of a function. Think of it like this. So imagine it's a composite function. Think of it like, for example, g of x. Let's consider g of x as maybe 4e x. And let's consider h of x as the function 3 log e of x. Yeah, you see this? And so isn't f of x just g of h of x? Do you see that? It's just the composite function. You're just putting it inside. And we know how composite function work, yeah? We know that the, first of all, we need to check if that composite function works. It exists. And we know how to do that. Remember, it's the range of the inner function. In this case, it's h. Must be a subset of the domain of f. So in this case, sorry, domain of h. What am I doing? Domain of g. My apologies. G is the outside function because I'm looking at this. Yeah. So what's the range of h? You remember your h is your log e of x. And remember, drawing a log function, the range is all reals. Is a subset. What about the domain of g? And we know that the domain of g is also all reals. Now, we know all reals is a subset of all reals. Is perfect. So this actually exists as a thing. And if it exists, remember that the domain of the composite function, basically f of x in this case, yep, is just equal to the domain of the inner function, and the inner function is h, which is basically what? Well, we know the inner function is this. What's the domain of this? It's basically, remember, to find the domain of any log, it's basically solving it when x is greater than 0. So solving the inside when it's greater than 0, which is basically, as we said, 0 to infinity. You see how easy? Same answer, but using our concept, using the knowledge that we've learned through methods, how to break that question down. It's really important to know how to do that. Beautiful. That's not bad. Next question, show that f can be expressed in the form of f of x equals 4x to the power 3. That's actually not hard. So for example, let's write f of x right now. f of x is equal to 4e 3 log ex. Look at the top, 3 log ex, yeah? Look at the top. We can take that 3 and put it to the power, yeah? Can't we? Because, for example, 3 log ex, what you can do is you can bring this 3 in here. Isn't that right? So that will be like that. So imagine doing that there. 4e log x to the power 3. Now, if you don't know this log law, it's important that you know. We know, so make sure you know this log law. It's that when you have an exponential and you have a log, can you tell this is the same base and this is the same base, yeah? And you have, let's say a, something like a inside here. It's going to be equal to a. These cancel out. If you have the same base here and same base, like in this case, yeah? It's going to be whatever it's inside, equal to what's inside, yeah? For example, in our case, can you see how it's e? Your base is e here, and the base is e. It's whatever it's going to be, x to the power 3, basically. So it'll be 4 x to the power on 3. And that's how we actually get that f of x is basically like that. Does that make sense? Really, really easy question there. So using the concepts that we've learned. Okay, so we can highlight that. Next question. Find the area bounded by the graph of y equals f of x, the x-axis, and the line x equals 1 and x equals 2. Now, you can easily graph this. This is not too hard. So you imagine, like, you don't even have to use the CAS here, but of course use the CAS to get the answer, but let's think about it. So for example, you have f of x. So f of x is, again, write it down. It's basically 4x to the power 3, which is a cubic. Now, be careful here. This cubic is restricted to this domain that we've said, 0 to infinity, yeah? So it's going to be like a, think like this. You have a open circle here, and like this. Because remember how normal it'll look like this, but, you know, we're going from 0 to infinity. Beautiful. So that's what f of x actually looks like. So that's your f. And basically we're saying, hey, we want to find out, let me draw it nice, actually. Let's say something like that. Yeah. For example, let's say this here is 1. So it says find the area bounded by the graph of f, the x-axis and the line x equals 1 and x equals 2. Imagine that's x equals 1 here. So imagine this is the line. Let's say just draw a straight horizontal line here. That's x equals 1. And that's the line x equals 2. And so basically what we're trying to find is this area over here. In this area over here. Isn't that correct? And to do that, it's really easy. It's just basically the integral from 1 to 2 of f of x dx. Isn't that correct? And beautiful. That's all we have to do. So let's go on our calculator and do that. So integrate 1 to 2 f of x dx, which is 15. So put that answer as 15. Beautiful. Or you can write, units cubed, because it's just area. It doesn't matter. You don't have to write that, but basically, yeah, that's it. All right, nothing else. Beautiful. The function g is an antiderivative of f that passes through the point 1, -5. Okay, so basically, the g is just the antiderivative of f. So when you antiderive f, it's basically your function g. And we also, of course, when you antiderive it, you know how you get that plus c? They've given us an initial condition to find that plus c. Okay, so we can actually graph g because we will have the whole function. Sketch the function g on the axis here over the domain d. You know your domain, which is 0 to infinity. So the same domain. Okay, so don't forget 0 to infinity. Label the coordinates of the endpoints, the x-intercepts, the points of the graph where x equals 1 and x equals 2. Beautiful. Let's do that in our CAS first. So what we're first doing is, we've got f here. We need to find g first. To find g, remember, it's just integrating f of x. Remember f of x, yeah? dx. You integrate it and then you get x to the power 4. But don't forget you have a plus c, yeah? So this here now is your, basically, g of x. Think of this as your g of x. Now, they told us a point of g of x that, basically they told us that when you sub in 1, it's equal to -5. Isn't that right? From that point. So what we can do is put it in basically here. So this will be here, will be -5 when your x values become 1. So 1 to the power 4 is just 1. And what we can do is we can solve answer, c. We found the c value. So going back to our original function, your c value is -6. Hence, your overall, now we can actually define g of x. Let me just define it as this function over here. Beautiful. Let's graph it using our CAS, of course. So, because that's what the goal is. So we can go to our CAS over here and actually graph g of x, yeah? Now, graph it within the domain they told us, which is x is greater than 0. Yep, enter. And this is the graph. Now, be careful. Make sure it's the same scale as your paper, so you can just copy and paste it perfectly. So go on menu, go Windows Zoom and Windows Settings. And for example, your x minimum in our case is -1, as looking at the paper. Your maximum is 2. They go by ones every scale. The y values is -10. The highest y value is 10, and the scale goes by 5. And you press OK, and this is what it looks like. And of course, draw some grids so you can actually copy and paste. You see, every box over here is the same as our paper, and so we can copy and paste every point. Absolute perfection. Let's do that now. Okay, so for example, we know that so the y value, of course, so remember what's g of x? Let me write g of x is x to the power 4 minus 6. So the y value is -6. So around here, so it starts around here. Starts around here. We know it passes through 1, -5, like there. We know it has an some x value over here, just looking at the graph. We know that the y value is so this here at this point it touches here, and we know when you sub in 2, it's going to be in 10, because basically 2 to the power 4, 16 minus 6 is 10. Beautiful. And then we can actually just kind of look at it like this. How perfect. Nice. So let me move this a little bit like there. This one over here is a little bit more like that. Okay, that's it. And so we are basically going to put a line that passes through all these points. Like that. Beautiful. Like that. Okay, so it passes through all those points, and it goes now be careful here. Be careful. This here point is not included. So make sure you put an open circle. Yeah, open circle here. Make sure it's an open circle, because they said, look, like x is from 0 to infinity, yeah? So make sure that, that's not included. And so what they told you is they sketch it over that domain, label the coordinates of the endpoints. Now we have an endpoint here, which of course is, 0, -6. What else? So label the coordinates of the endpoints. The x-intercept, now the x-intercept is going to be easy, and the points of the graph where x equals 1 and x equals 2. So at x equals 1, we know it's 1, -5 from here. And at 2, which is here, we know it's just 210, as we said. So 210. And we also need to label the x-intercept. To find the x-intercept, you remember, just let g of x equals 0. So go back to our graph, our CAS, so solve g of x equals 0, comma x, and so we get this here, which is basically the 4th root of 6, basically. You can write it like that, yeah? The 4th root of 6. So let's write that down. So the 4th root of 6 is 0. That looks perfect. So have we labeled everything? We've labeled the coordinates of the endpoints. Make sure it's an open circle within that domain. The x-intercept, the point where x equals 1, and x equals 2. Perfect. That is it. That's how the graph should look like. Hopefully that's correct. I haven't missed anything. Nice. Okay. Next question. Let a be greater than 0.5. Find the area bounded by the graph of f of x, the x-axis, and the line x equals 0.5 and x equals a, and can be expressed in the form of GA plus b. Find the value of b. Now, again, what is g of x? Oh, what just happened there? We know that g of x is what? We know that g of x is what? So g of x is x to the power 4 minus 6. Isn't that correct? Okay, that is it. So what we need to do is we need to work through this. Okay, so basically, f of x, redrawing it actually, taking this graph here, imagine just copying and pasting this here. Duplicate it, going back here. Like that. Okay, so it says the area bounded by the graph of f of x, so we have f of x, the x-axis, and the line x equals 0.5. Imagine now if this here is, let's rub some stuff out, imagine this here is 0.5. So that's x equals 0.5, and x equals a, because we know a, so it's going to be some here, because we know it's going to be greater than 0.5, yeah? Can be expressed in the form of this. So, okay, really nice. So, basically, like, to find that area, it's just the integral from 0.5 to a of f of x dx. And so that's going to give me the area. And that's going to be, they told you the area is going to be in terms of, it's basically going to be equal to this GA plus B, like this. GA plus B. And we want to find B. Before we do most of the work here, our CAS is going to do all the work, by the way. We know that, for example, this is G of X. So G of A is what? It's a to the power 4 minus 6. We can actually just kind of rub this out and write that a to the power 4 minus 6. But don't forget plus b here. Because you remember this here is your G of A. Don't forget that plus b, and that's our goal. And we can put this in our CAS and basically let the CAS do the work for us, like solve it. Let's go. So we go on our CAS, and we would basically, what we want to do is solve the integral from 0.5 to a of f of x dx is equal to a to the power of 4 minus 6 plus b, comma, b. Which, damn, we don't want it in decimal places. That's where the comes out. So what I'm going to do is, to make sure it's not, I will just do it by hand. So, for example, I'll take this over here. I'll integrate. Why is it really f of x? I think it's because I'm putting 0.5 here. What about if I put a half? There it is, there it is. Okay, so if I put a half, which is just the same, so let's write that down here. So that what this simplifies to. So 16 a to the power 4 minus 1 over 16. Yep. Which you can kind of simplify it more, like, you know, so it'll be basically a to the power 4 minus 1 over 16, basically. Yep. So that here is this over there equals that a to the power 4 minus 6 plus b. Now we can see that, you know, the a to the power 4 here is a to the power 4 here. So what is, how can we calculate b? Well, we know that this here equates with this over here. So it's going to be negative 1 over 16 equals negative 6 plus b. So let's put this in our calculator and we will get our b value. Easy. So, negative 1 over 16 equals negative 6 plus b. And we solve answer, comma, b, which is 95 over 16. That is your answer. 95 over 16. Beautiful. So that looks correct. Let's just double check it by pressing Control Enter, actually. So 5.93, it's the same as the other one, yeah? Yeah, 5.935. So absolute perfection. So that looks nice. Easy. So it's find the value, yeah. Next question. Consider the function h, where you're going from 1.5, the domain's from 1.5 to infinity, where h of x is basically f of 2 of x minus 3 minus f of x. Find the quadratic expression for h dash of x. Okay, this is not too bad. So if you just go on your CAS and let's define it. So h of x is basically defined as f of 2x minus 3 minus f of x. Yep, just double checking if I have not made any mistakes in defining it. Beautiful. So of course what we want to do is we want to derive h of x. And this is the quadratic. Absolutely perfect. So we can write this right there. Okay, so it'll be h dash of x, 84 x squared minus 288 x plus 216. Okay, that looks the same as what we have on the calculator. Perfect. Perfect, that's it. Nice. Hence, so using that, or otherwise, find the coordinates of the point where the graph of h of x, where the gradient is a minimum. Now look at the wording. They've even highlighted it for you. We want the gradient to be minimum. So this is our gradient function, yeah? Yep. So we can kind of do this. So for example, to find so imagine this is your gradient function. So h dash of x, yeah? This is your gradient function. Gradient of function. We want this gradient function, we want a minimum, like we want the minimum of this gradient function. Basically, you know how to find the minimum point. We normally derive it, let it equal to 0, and that's what we're going to do here. For example, what I'm going to do here is derive this gradient function, because that's where we want to find a minimum of the gradient. So it's basically finding the double derivative of x and letting it equal to 0, basically. So let's go to our CAS and do that. So for example, re-deriving this here, putting it over here, and letting it equal to 0, and we can basically solve this answer, comma x, we get x equals 12 over 7. Now, be careful. We don't know if this is a minimum value. Oh, yeah, it is. What am I even saying? Actually, no. But let's be careful here. We can double check it by doing this. We can go menu, calculus, and we can go to minimum function. And to double check if it is the minimum, I just want to be 100% if it's a minimum. I will take, you know how we want the minimum of your gradient function, so this, comma x, comma, remember how there's a domain, it's 1.5 to infinity, basically. And it will help me, it will give me where the smallest value is. Yeah, it is. So x equals 12 over 7 is the minimum value. Perfect. So, and you could also graph it if you want. So, for example, well, you can also graph it. If I graphed it, nope, I haven't graphed it here. So, for example, you can graph it, and you can see it's a, if I go down here, it's a minimum point at that point. Does that make sense? Make sure you restrict it, by the way. My apologies. Make sure you restrict it to x is greater than 1.5, which is, look, you can see that that's where the minimum occurs. So, keep that up. We found like the minimum point is at 12 over 7. That's the x value, but we want the coordinates, yeah, of h of x where the gradient is minimum. So basically, just so you know how h is the function, to find the y value, sub in where this is the x where the gradient is a minimum, and this is the y value. So this is your x value, and this is your y value of your coordinates. So let's just show some working out too. So for example, when we did this, we got, when we derived it, double derivative, we get this minus 20. I'm just copying it from my calculator, where x is equal to 12 over 7. And then I sub it back in to our original function. We got negative 972 divided by 49. Hence, your final answer, so the coordinates is what? It is 12 over 7. So 12 over 7. Negative 972 over 49. That is perfect. Okay, let's highlight that. All right, that looks nice. Next question. Over the interval from 1.5, so from our domain 1.5 to some value p, where it's inclusive, the gradient of h is strictly decreasing. Find the largest possible value of p. That's actually not too bad, because we actually have the graph. Let's go back to the graph here. So let's think about it. Oh, not this graph. Here, yeah? Can you see how this is 1.5 to infinity? And we want to find p. P is like the x value where, okay, when's the function decreasing? Well, it's decreasing from 1.5. Can you see how it's decreasing, the gradient, decreasing, until we hit the turning point. What had just happened? What? Don't tell me. No. How do I get rid of this? I'll put it like that. Okay. No. Don't know what that is. Just leave it there, Bob. Okay. So, for example, do you see here? That's 1.5. That's an open circle because, you know, it's non-inclusive. All the way. Can you see how it's decreasing until we touch the stationary point or the turning point? That's where the, and it's inclusive. That's where the p-value, that's your p. Basically, that's the largest value of p where your gradient function is strictly decreasing, yeah? Because after that, it's strictly increasing. Do you see that? So your p-value is basically the minimum turning point, which we just calculated, wasn't it? 12 over 7? Yeah, it was 12 over 7. 1.71 is 12 over 7, yeah. Yeah, 12 over 7. So that's your largest p-value. That's actually not hard. If I haven't done it yet, 12 over 7. Beautiful. So 1 mark there. Beautiful. Next question. Question 3. Let h of t be this function where t is greater or equal to 0. The function h models the water height in meters. On a tide height marker at the base of the boat ramp, the variable t represents the time in hours after midnight. So midnight is 12 a.m. So 12 a.m. So 12 a.m. on one particular morning, Monday morning. For example, t equals 6 represents 6 a.m. Yes, true, because, So, on this Monday morning. Perfect. All right, so not too bad. So we've got this height marker. Okay, and the tide goes up and down. Okay, part of the graph of h is shown. What the hell is this? And it makes sense because you got two sine functions basically being added together. It's like addition of ordinals, basically. So it's going to look like this. Find the water height at 6 a.m. on this Monday morning. Give your answer in meters correct to 2 decimal places. Not too bad. We know it's basically 6 a.m. is basically t equals 6, as they told us that already. Yep, isn't that correct? Yep, 6 a.m. So it's basically, we're just trying to find basically h of 6. So we can just go on our calculator and kind of do that. So first of all, control N this whole thing. Let's make a new calculator. So, what's the function again? It's, let me define it first. So h of t. Alright, so h of t equals 2 sine, 4 pi times t over 25 plus 1/2. So 1/2 sine 3 pi times t plus 3. And all we're trying to find in this example is h of 6, the height at times 6. Control Enter to 2 decimal places. It will be 3.25. Let's write that down. 3.25 meters in this case. Yep, is it meters actually? Yes, in meters. Yep. Not bad. Next question. Find the average height of the water between 6 a.m. to 6 p.m. on this Monday. Give your answer in meters correct to 2 decimal places. All right, so we're finding the average value in this case. So the average height. So again, 6 a.m. is t equals 6. And 6 p.m. is like you're adding 12. Like, for example, going from 6 a.m. to 6 p.m. is just adding 12 hours. So what's basically 6 plus 12? It'll be t equals 18. So that is it. So if basically to find the average height, remember, so average height is, so your average height is 1 over b minus 2, so it's 18 minus, basically 18 minus 6. The integral from 6 to 8 h of t dt, which gives me what? Let's go on our cast and do that. So it is 1 over 18 minus 6. So the integral of 6 to 8. So 6 to, what did I write? 8, sorry, 18. I apologize. It's supposed to be 18. 6 to 18 h of t dt. Enter, control Enter, and we get 2.9 thing. So we want it to 2 decimal places, so it'll be 2.9, basically 2.98. 2.98 meters. That's your average. Beautiful. 2 marks. Nice. Question. A boat requires a water height of more than 1.4 meters to be safely launched off the ramp. Between 6 a.m. to 6 p.m. on this Monday, find the total amount of time when it is safe to launch this boat. So the total amount of time. Give your answers in hours correct to 2 decimal places. Okay, so we want the total amount of time. Okay, so from 6 a.m. to 6 p.m. Well, let's have a look at it from the graph. 6 a.m. So you remember 6 a.m. is, here at this time t equals 6. And 6 p.m. is at 18, like this. And basically, it's the height, or what is it, 1.4? More than 1.4. So let's just draw a line that represents 1.4, which is, so for example, this height here is, it looks like halfway, but imagine 1.4 is a little bit smaller, around there, like that. Somewhere, let's say that, let's estimate that's 1.4. Doesn't matter because we can just graph with our calculator much better. So what we're trying to find is this time here. So it's the, can you see the line, which is 1.4? We're trying to find where the water tide is greater. So for example, it's going to be in the sections over here. Like you can see this section over here. This section is all good because it's above that. This is where it's safe until you reach this point over here. Again, it's safe all the way from this part to this part too. It's also safe from here all this way, all of these over here. It's all safe until here. Yeah, so from like 6 a.m. to 18 p.m., all the places that we've highlighted, so all these over here, which is above it, is the safe time. And we need to find that time where it is, safe. So the total time, which we can easily do. Let's actually graph it. This is not accurate, of course. I'm just trying to visually show you, but we're going to actually go in our cast and do this. So first of all, let's actually graph it. So I'm going to go on my graph and I'm going to graph h of x, of course, from that domain. So we're going from 6 a.m., which is x, to 18, yeah? And enter that, and this is with a graph here. Beautiful. Now I'm going to draw the y equals 1.4. There it is. So again, going back here, I'm going to zoom in, and this is what we want. So we have how many point of intersection? We have 1, 2, 3, 4. We have 4 point of intersections, yeah? And look, these are all the sections that we want. The time from here, all this time until here. Then, of course, you have a little section here that's dangerous because it's below that 1.4, not this section. But then from this section to this section, and then this section to all the way to 18. Makes sense? So first, let's solve those to be exact, those values of time. So it's basically, we can just solve, what did it was, capitals? So let's solve h of t equals 1.4 comma t, of course, from that domain, which is 6 is less or equal to t, less or equal to 18. Enter. And so look, we have 4 times over here. Perfect. So the first time is, of course, this is 6, but this is the time here is 6. So it's the first point, this first point minus 6. So it's this point here, the first point minus 6, and this is it's 1.8. So the distance from here all the way here, so the time from here to here is 1.8 hours, which is actually, yep, safe. Then you've got the dangerous here. This is the dangerous part because it's below, so we don't take that. And this is the safe part where it's the second intersection and the third intersection, so minusing those times. So your third, so this is your third minus your second, and this is the time difference from here to here, so that's safe. Then from here, it's all below, so this is a dangerous, we don't take that. And then from here, your last intersection all the way to the 18, t equals 18, this is all safe. So 18 minus the last, so 18 minus the last point of intersection, which is this. And so it's 7.36. So this is all our total time where it's safe from 6 a.m. to 6 p.m. We can add those all up. Enter, and this is your total time. Now they told us how many, what did I tell us again, going back to the question, two decimal places, so it'll be 9.47. 9.47. So let's okay, we haven't even showed any working out, but yeah, it's really not hard. So so what I would do to get those 2 marks, of course, is first of all what we just did, which is solve h of t equals 1.4, and we found out that the times is where, and I'm going to write those times, of course, the times where I'll write it to 2 decimals, so 7.8 t equals, because you need to show some working out here, so 7.4 t equals 8.27, t equals, the last t is 10.66. And remember, how did we do it? So we said that the total time, so t total, so the time in terms of total is, we said that we minus 7.8 minus 6 plus, then we minus 8.27 minus 7.94 plus, then 18 minus 10.66, and all of this gave us a total of, what was our last final total time? It is basically 9.47 basically hours in terms of the total time. Hope that's correct. That looks not too bad. That's not a bad. Oh, let me highlight that much more larger. There it is. Okay, next question. Find the absolute maximum height of the water on this Monday after 6 a.m. and the time when it occurs. Give the height in meters, correct to 2 decimal places, and the time correct to the nearest minute. Okay, so we want the maximum height. Now we need to look at the domain here, because when does the maximum height occur? Well, first of all, you need to realize that it says on this Monday, yeah? So for example, we know that the start of the Monday, we know that the start of the day on the Monday, it starts at 12 a.m., yeah? So imagine this is your Monday. And then the Monday ends at 12 a.m., like the next 12 a.m., because it goes to our next day, of course, yeah? So you have this whole section over here. Now we're saying, hey, find the absolute maximum of the water after 6 a.m. So after 6 a.m., basically like here, that's 6 a.m., so 6 a.m., so this here, from here to here, it's 6, like basically 6 hours. So basically we're saying, because we want it on Monday, we basically want to find the maximum height from this domain, from 6 a.m. all the way to 12 a.m., which is basically a difference between 18. So what is it going to be? In terms of time, so we're saying basically, kind of writing it nicely here. So we're saying from 6, this is t equals 6, all the way to t equals 24, because t equals 24 is the next day, like where Monday is now going to start changing. It's going to be the next day, because so we need to make sure we have the right domain, and we can just use the cas here really quickly to get this. We can use function maximum. So we've got this. We've kind of got the domain. We can just go use our cas now and actually find the maximum height. So let's do this first by cas. Of course, by cas, what we can just do is go to menu and go to calculus and go to maximum, function maximum. Write the function, comma t, and write the domain where you want to find it. Well, we said after 6 a.m. and it's only on Monday, which is from 24. Enter, and it gives me the value of time where the maximum occurs. Absolute perfection. And so we've got the time. We also want the actual height. So h and subbing that in. And this is your height, of course. So these are your answers. So let's write those down. So for example, your height max into 2 decimal places is basically 5.2. So 5.2 meters. And your time that it occurs, that maximum time, that time is, it's 15 hours. So 15 hours. But it says, and the time correct to the nearest minute. So we also want the nearest minute. Going back to our cas, to get the nearest minute, of course, it's just 0. Where's the time? 0, this whole thing here. So this decimal here times 60. So it's basically 30 minutes. The nearest is 30 minutes. So 18 hours and 30 minutes. That is your answer, basically. Now, of course, to be honest, first of all, there isn't a lot of working out. I haven't done a lot of working out here. It's just because I just make sure I restricted them. Normally, of course, we want to show some working out that's more appropriate. So, for example, what I would do is, of course, to find maximum height, we just, of course, derive it. We can derive h of t, and which is going to give us what? Let's first derive it. First derive it. So, in terms of time, h of t. Yep, of course, and we write that, and then what we're going to do, of course, we will solve it, let it equal to 0, and solve this whole thing over the time. So solve this comma t, so comma t over the time 6 less or equal to x, less or equal to 2, less or equal to 24. And as you can, there's a lot of times, but we know that the max height occurred. There's a lot. Oh my God. Because you don't realize there is actually a lot of minimum points, of course. I mean, you can just virtually look at it in the cas anyway. If I just restrict this to 24, get a little bit zoom out. That's not very useful. So zoom out. The maximum height occurs somewhere here. So you can just go menu, analyze maximum. There it is. So the maximum height, that's correct. That's what we got, 5.2 and the time. So yeah, all to basically get the marks is I would just write this derivative, let it equal to 0, and get my values, and that's it. Let's do that. So h of t is basically going to be, I'm going to write the whole thing, so it'll be 3 pi over 5 cosine 3 pi t plus 8 pi 25 cosine 4 pi t over 25, and of course we want that all to be equal to 0, and that's it. So I think just writing the derivative function, letting it equal to 0, and we get the times. That should give you all the marks. Easy. Next question. Show that h of 25k equals to 3 for all positive integers k. Okay, so basically we're trying to show that when you sub in 25k into the function, it will always result in 3. So I think it's a show question. Let's do that. So the way that I would show this is actually subbing it into the function at first. So for example, our function is, oh my God, going back. Let me just write it down. I'm going to open my cas and write the function. So the function is, I'm going to write it. So basically h of t is equal to basically 1 over 5 sine 3 pi t. So I'm just using my cas plus 2 sine 4 pi t over 5. So over 25 plus 3. So this is our function. Just double check it. Okay, so it's basically the same thing, but yeah, written just these are swapped. It doesn't matter. So yeah, just double checking it again to 1/5. Beautiful. So what happens if you sub in h of 25k? what happens is, you would sub it in all of the values. So it'll be 3 pi, 25k here, plus 2 sine 4 pi t is 25k over 25 plus 3. And so that's going to simplify to what? It's going to simplify to 1 over 5 sine 75 pi k plus 2 sine, those 25s are going to cancel out, so about 4 pi k plus 3. And I think you can see what I've seen here. Okay, first of all, this here, think about it. We know that they say where k is basically positive integers. So basically where, of course, k is an element, all integers but positive. So positive integers means like 1, 2, 3. For example, if you sub in 1, into this, it'll be like, sine 75 pi, which we know is 0, because we know that, like, for example, sine, so we know that, for example, this, let's break this apart first. Sine 75 pi k, it's just the same as like writing like sine pi k. Does that make sense? It's the same thing, It's actually the same because think about it like periodically. For example, if you draw a normal sine function, So of course the period here is 2 pi's. That's pi, that's 0, and that's so for example, if then 3 pi. You can see like for all, like you see how that's this here. What would this give you? It will always give you like in other words, like odd values. Like for example, it's the same as 75. Oh my god, that's actually a little bit hard to explain because I'm trying to just show how it's just the same thing. For example, if you sub in k equals 1 in this case, it'll be sine 7 pi. So 7 pi. And this 7 pi is basically the same as like, think of it as like drawing a normal sine function. Imagine like for so long, but then when you reach, you're going to have, like this part would be like 74. And then of course, it'll be 75. Basically, it fits this formula, basically. It fits this periodicity where this here is odd. It's always going to give you those odd, not odd, but it always gives you, this here is equal to sine pi because of periodicity. It's so hard to even explain. How would you, like, it's not hard to explain in paper because we know that they're equal, But there, does that make sense? So we know that this here, always, is the same as this over here, which we know that sine pi k is always going to be 0. Like, for example, if you summon k equals 1, it's sine pi, which is 0. Then it's the 2 pi, 0, 3 pi, 4 pi. It just goes to 0. It's always 0. So we know this whole statement is basically equal to 0. What about this over here, sine 4 pi? The same thing. Isn't that true? Like, for example, sine 4 pi k, For example, if you subbed in 1, like, if you... It's kind of the same as saying, like, sine 2 pi k. Like if you subbed in 1, if you subbed in, for example, 1 will be 4 pi. If you subbed in then 2, it'll be 8 pi. It's still 0. All those values output 0. Does that make sense? So it's like basically the same as this. So it's just equal to 0. This whole thing and this whole thing just always output 0 for any k as a positive integer. So does that make sense, everyone? So if we know that, we know for a fact that this is going to output 0 plus this is 0. And so you're just going to left out with this 3. And that's why it's always going to give us 3. Makes sense? So what I would kind of do here is I'll take this here. And I'll duplicate it. Put it right over here. And I say, hey, this part here is 0. And you got a plus. And this part will always result in 0. And don't forget that plus 3. Hence your overall h of 25k equals always 3. Does that make sense, everyone? It's not hard, but it's so hard to explain the periodicity. Does that make sense? Because like for example, just sub in your calculator. Like if you put k equals 1 into this, it'll be 7 pi k, which is just of course 0. Sub in 2, 0. Sub in 3, it's always going to be 0. Does that make sense? So that's how I would have approached that question. Find the period of the function h. Now going back, look at the problem. It's actually harder than like you. It's not just 2 pi over n because both of them have a different inside value. So by the way, it's actually not hard to find the overall period because say for example you have two two trigonometric functions that have different periods. How do you find the period? It's actually not as bad as you might think, because I think I've saw this kind of question. They've started putting these types of questions in, especially 2021 papers. There was a 2021 paper that had the kind of same question where you had to find the period, and there's a way to do it. And this way is a really cool way. So what you just need to do is to find the period of each individual periods for every trig. Like for example, you have this here, we want to find the period for h of t. So we got to find the period of this and the period of this sign here, both periods. So let's do that. Let's call this here, let's say T1. Let's call this the period. Let's call this period 1, which is of course 2 pi over 4 pi 25, which is just basically 2 pi times 25 4 pi, which is 25 over 2 overall. 25 over 2. That's your period here for this one. Period 2, the same thing. So it'll be again 2 pi over 3 pi basically. The other one, which is basically just 2 over 3. Look, do you see how we both 2 over 3, sorry. We found the period for both of them. And to find the overall period, you just need to find what we call the lowest common multiple. The lowest common multiple of these two values, and that's going to give you your period. And guess what? Your CAS can do that. Let's go in our CAS, and we can just go to menu and just actually go to number and just go least common multiple, and write those two values in. So we want to find the least common multiple of 25 and 2, and 2 over 3. Oops, 2 over 3. So 2 over 3. Like that. Enter, and this should be your period. Now we need to double check it. Let's check if it's the period. Like for example, if I subbed in h of, for example, 1, yeah, h of 1, it's this value, yeah, 3.95. So imagine I plus 50. You know how the period's 50? If I plus 50 on that one, it'll be 51, yeah? So if I subbed in 51, it should still give me the same, 3.96. It does, yeah? Do you see how it fits the formula? That is your period. It's 50. So beautiful. So your period, in this case, is 50. Beautiful, so 50. All right, because I learned this actually from one of my friends. He's actually, does tutoring, and he just told me about this, and it's so cool. It really helps out a lot to know this method here, the least common multiple. Beautiful. Next question. Question 4. We're done with that. Yeah, question 4. Let's have a try at this question. A claim is a request to an insurance company for payment after an incident. Company A offers car insurance. Let X be a random variable representing the claim amount in thousands of dollars for each claim to insurance company A. The probability density function of X is given here. Okay, find the mean claim amount in thousands of dollars. Okay, so basically, yeah. Okay, so to find that, it's basically to find the mean for a continuous random variable. It is going to be, so your expected value of X, which is going to be the integral from, we're going from 2 over 3 to infinity of, it's in terms of, so x times f of x dx. So put that in our CAS calculator and we should get it. It's only 1 mark. So let's control N this whole thing here and go add calculator, and we can, just define f of x. Define f of x as basically just 8 over 9 x to the power of 4. Where we know that the expected value is 2 over 3 to infinity, where x times f of x dx, which gives us 1. So the answer is 1. Yep, in thousands of dollars. Beautiful. That looks correct. Yep. That's it. Next question. A claim of more than $2,000, that is x is greater than 2, is classified as large. Find the probability that the claim is classified as large. Really, really easy. Just do it in your CAS again. So basically what we're trying to find is the probability that x is greater than 2, which is basically, of course, the integral to 2 to infinity of f of x dx, which will give us, let's do that. So I can just recopy this here, take the x out here, and put a 2 here, enter, it's 1 over 27. So that's the probability of being classified as large. 1 over 27. Next question. Given, so whenever they hear the word given, it's already telling me that's probably some conditional probability. Given that a claim is classified as large, find the probability that it is more than $4,000. So it is, again, conditional probability here. So we're basically saying, hey, find the probability that it's classified more than $4,000. So remember, it's in, like, for example, 2,000 represents x is greater than 2. So 4,000 is basically x is equal to 4. So given that it is more, so x is more than 4, so that's 4,000. Given that the claim is classified as large, and we know that to be classified as large, it's basically x is greater than 2. And of course, we need to use the conditional probability formula, which is, remember, finding the intersection between these two, which you can just draw a normal little nice number line. For example, 2 is here, so open circle going to infinity, and 4 is here, open circle going to infinity, and we can see the point of intersection is here, which is the probability that x is greater than 4, and then divided, and you always divide it by the probability. Divided by the probability of what's on the right. X is greater than 2, and of course that's easy. So we know, just do that in our cast. For example, what I'm going to do is we need to divide. I will take these two here. So I'll take this one over here too. So that here is when it's large, so x is greater than 2, perfect. And we want divided, like, then this has to be 4 to infinity. So look, probably that x is greater than 4 is that, and probably that x divided by x is greater than 2, enter, and that gives me 1/8. Really, really easy question there. Okay. Put that there. Okay, done. Next question. In a random sample of 10 claims, find the probability that more than one claim is classified as large. Give your answer correct at 3 decimal places. So this is just binomial. Now we're dealing with binomial variables. So I'm going to say let x be binomially distributed, where how much we have? We have 10 claims. And the probability that a claim is large is, remember, we calculate it to be 1/27. That's the probability of success for it to be large. So what we're saying is, hey, we're trying to find the probability that x is, that the probability that more than one claim, so greater than one claim, is classified as large. Which we can write, of course, this as greater or equal to 2, because it's binomial. And so we can put that in our cast and get the answer. So go on menu, go to probability, distributions, and we can go straight away inverse CDF. So we're going from, of course, 2 to the max, which is 10. The number of trials is, of course, 10, and the probability of success is 1/27. And so we press enter, and we get this over here. So to 3 decimal places, it is 0.051. So let's write that down. So 0.051, which is there. Nice. Question 4. A household has two cars insured with company A. For each car, there is a 20% chance that a claim will be made next year, independent of the other cars. So they're independent events. Okay. The claim amount are also independent. So, okay, that's also independent. Okay, that's easier to deal with when they're independent. So at most, one claim can be made per car next year. Okay. Find the probability that next year, in this household, there's at least one claim classified as large. I'll give you an answer to 4 decimal places. So the way I would approach this question is there's so much information happening here. Because as you know, what I'm going to do is I'm going to draw a probability tree diagram to kind of relate all of them. Now be careful. Normally a probability tree diagram, you use it for when you have, like, for example, you know, not independent, like you use it, because we're dealing with independent events, you know, let's take all this information and put it in like a tree diagram, and because you can easily visualize what's happening, because it's so much information. I'm not understanding what's happening here. So yeah, we want to make sure we do that. So okay, we have 2 cars. So imagine we have, I'm going to draw 2 cars here. Let's consider that as car 1, car 2. Yep. And then what they do is they try to claim them. So, okay, so for example, of course, when you claim, so there's 2 possibilities for claim. You can, of course, claim. And of course, you fail to claim, so claim not. And of course, the same with this over here. So let me just copy that and put it right there. And of course, when you claim, you get 2 possibilities. Remember, you can get a large payout, which is the x is greater than 2. That's what we were saying. So you can get a large, or you can get a small. And that's only if you get claimed. So look, that here, you can put it with only the claimed, yeah? You see that? That's so much easier to possibility. Now, of course, like these are not related, as you can see, these are not related, they're independent. So you don't actually, it's silly to have that here. You can just separate them. So you have like two events here. So like, for example, that is by itself, that's independent, and that's of course independent itself too. Okay, now they told us that the probability of, what did they say? For each car, yep, there is a 20% chance of a claim will be next year. So if we're dealing, all of these are being next year anyway. So if we want a claim, so we know that there's a 20% of a claim. So for a claim, it's going to be let me use a different color. So 0.2. And so it means unclaimed 0.8. It's the same with this one because they're independent. So it's the same probabilities. And of course, we know that if there is a claim, we know that the probability of getting a large is 1 over 27 from the last question that we did. That is what's the probability of getting a large. So this has to be 26 over 27. And the same with this over here. It's going to be all the same. Okay, you see that? Okay. Now, oh my God, it says, so find the probability that next year, so we're doing all next year, in this household, there's at least one claim classified as large. Okay, because there's many possibilities, yeah? If we want like one claim to be classified as large, let's talk about the possibilities. So that's the probability, like you can have, of course, car 1, that it, claims and it gets a large. Good. It perfectly does it. So car 1, it claims and enlarges, and whereas car 2, of course, has to, it can fail. So it doesn't claim, or it can claim it, but it can become small, so not large. So, for example, that is one possibility. Like all of this here is one possibility. You can also, because remember, that's what it is. So you're saying at least one claim. So for at least one claim, you can, of course, to write it nicely. So, for example, you can get car 1. Let's call it C1, that it's claimed as large, by the way. Think of it like that. So, for example, you can get car 1 to claim, intersection, of course, car 2 does not claim, yeah? That's one common, because that's at least one. So look, you got one. And of course, it could be vice versa. So you can also do like C2 is claimed, but whereas C1 is not claimed. Or you can get both of them claimed, because it's at least, so the max is 2. So yeah, you can get basically both of them claimed. So like claim 1, intersection, claim 2. Does that make sense? So all of them get claimed. And that's what, but that's a lot of probabilities to calculate, because what we can just do is, why don't we find the probability that both of them don't get claimed, and then 1 minus that. And so we will get all of these probabilities. Isn't that smarter? Yeah. So why don't we just do this? So for all of these here, it's just equal to 1 minus the probability that both don't get claimed. So car 1 does not get claimed, and car 2 does not get claimed like as large. Yeah? And what is that though? Like what is that? Probably that car 1 does not get claimed, and car 2, car 1 does not get claimed, and car 2 does also not get claimed. Now we know that they're independent events, yeah? So remember when you want to find an intersection, it's just the probability of car 1 times the probability of car 2 not getting claimed. What is the probability that car 1 in this case does not get claimed? Well, let's have a look at the possibilities. So there's 2. For example, car 1 can claim, but then it's not large. Yeah? So it can claim, but it becomes small. Or you can have another possibility where car 1 just doesn't claim. So it has 2 possibilities here. So let's do that. So for example, so we can say, so it can claim, so 0.2 times 1 over 27 plus that it doesn't even claim, so 0.8. That is that probability. So that is that times, that's for car 1. And imagine doing it for car 2. It's the same thing, yeah? So it's all the same stuff. Again, so for example, you can get car 1 claim small, or car 1 doesn't even claim. So it's just the same probability. Because it's the same probability, we can just square it. Square it. And so that's what that's what that would give me. So yep, so that will give me that probability that, both of them don't get claimed as large. And so we just remember our final answer, what we want is to be, find the probability. So it's 1 minus that probability, by the way. So 1 minus the probability of both cars don't get claimed, which is equal to 1 minus this whole thing over here. Imagine copying and pasting that in our calculator, this here. And that should give us our answer. That's an ugly ass question. That's like, there's a lot happening here, but if you kind of break it apart, yeah. So let's do that in our cast. So 1 minus 0.2 times 1 over 27, so times that, plus 0.8 And don't forget you square. Which is does that look right? So correct it for the so 0.3 0.2 times 1 over 27. My god, what did I do? I made a little mistake. Oh my god. No, come back to the paper. So this is supposed to be 27. Oh my god, what? So 26, sorry, 26. Does that make sense? Because you remember when we said car 1 claims and does become that probably is 26 over 27. What 1 over 7? What did I do? Wow, that was a little simple mistake that could have got it all wrong. So just make sure you double check your answer. Let me double check 0.26 1 over 7. Then that should work, yeah. Let's try that. That's nearly kind of the same answer. So if I put 26 over this, because that doesn't look like I'm 1 over 27, but we're not claiming it. Okay, just let's also double check. 1 minus 0.2 times 26 over 27. You said, look, that's probably, yep, claim times, it becomes small, or then unclaim, and you square that. Okay, perfect. That looks correct. So to 4 decimal places, it's 0.0148. Let me write that down. That's a hard question. Like, it's not hard, but it's, I don't know. It just breaks your head. 0.0148. That looks nice. Okay. Not too sure actually. Still, though. So let TA be a random variable that approximates the time taken in days for a company to settle a claim. TA follows a normal distribution with a mean of 32 and a standard deviation of 7. Find the probability that TA is less than 45. What a beautiful question to 3 decimal places. Okay, so we can just, of course, go on our calculator, go to menu, probability distributions, go to our normal CDF. Of course, we're going negative infinity to 45. Your mean in this case is 32, and your standard deviation is 7. And press enter, and you get your answer. Now to 3 decimal places, it's 0.968. Let's write that down. 0.968. I love normal distribution. It's just so much fun. Company A settles 99.5% of the claims within K days. Find the value of K. Give your answer to the nearest whole number. So basically, if you draw a normal distribution here, like that. So K is going to be somewhere here, and we know that here, that all of this here, this probability here, that is 0.995. They look, a company settles 99.5% claims within the K days. Find the value of K. Basically, yeah, use inverse norm in our calculator. Go menu, go to probability, distributions, inverse normal. Your area, of course, is 0.995. Your mean value, again, was 32. Your standard deviation was 7. Enter. And you get basically to a whole number, just 50. Okay. Beautiful. Next question. Company B also offers an insurance. In a random sample of 80 claims to Company B, 76 were paid. Find the approximate 95% confidence interval for the proportion of claims paid by Company B. Give your answer corrected in the, to 3 decimal places. Of course, we can do that. Just use your CAS to find confidence interval. Let's do it. Menu. Statistics, confidence interval, and go to 1 prop Z interval. And of course, the number of successes they told us that 76 were paid out of the 80, and we want the 95% here. So press enter, and so here is your C low 1, C upper. Of course, we want it to 3 decimal places, which is 0.902 and 0.998. Okay, let's write that down. So it's only 1 mark, so just write your answers. So 0.902. 0.998, and that looks perfect. Okay, yep, nothing that looks fine. These are beautiful questions. Okay, next question. So for let TB be a random variable that approximates the time taken in days for company B to settle a claim. Suppose TB follows a normal distribution with a mean of 25 and a standard deviation of 5. The probability density function, T of A, is here, so it has a mean of 32 and 7, is shown on the axis here. Sketch the probability density function for T of B, which is, of course, has a mean of 25 and that on the same set of axes. What a beautiful question. Actually, I love these types of questions because they're quite not hard, like if you actually understand them. So what I'm going to do is, it's really easy because we know that the mean is 25 and the standard deviation is smaller than, this one over here. So it's going to be much more thinner. Now, what I'm going to do is I'm going to be a little bit cheeky. Not cheeky, but just we know that, for example, to draw the function for a normal distribution is this. Make sure you have this in your, bound reference, especially in these. It always comes up on exam 2, by the way. 1 over theta square root 2 pi e to the power of negative half x minus your mean over your standard deviation, L squared. Okay, so this is your formula to kind of convert. If you have your, your mean and your standard deviation, you can put them in this formula and you can actually graph it using your CAS. And so this is actually very, very beneficial because think about doing that for this one over here and do it for this one over here. And you can actually compare what they look like. And you can kind of just copy and paste them on your paper. So for example, let's do this. So what I'm going to do is go on my thing here and let's go graph. And so I'm going to graph the first one. So 1 over... So your standard deviation for t of a is 7. So it'll be 7 times 2 pi e to the power of basically negative half, so negative 0.5 we can say, x minus your mean. So x minus your mean is 32 over your standard deviation, which is 7, all squared. Easy. I'm just gonna copy that because I'm gonna need it for the next one. And look, I press no. Yeah. Luckily I copied it. There it is. So that's what it looks like. Now you can see it because it's not one of the most visually looking thing. But if I kind of scale it within my looking at my paper, look, the x-axis is scaled from of course 0 to, for example, like 55. It looks like so 55, and probability is so small. So like half. You can put half. Yep, you can see a little bit curving. 0.1. Also make this 0, so make that 0. Okay, perfect. This is what the graph looks like. It looks like this. It looks beautifully. So that's what it looks like. Imagine then kind of making another one, which is the one that we want, but it has a standard deviation of 5. Put a 5 here, put 5 of course here, but your mean value is 25. So look, do that. And this is our red graph. Let me move this away. And guess what? Imagine, so you've got this here, the original graph, and now graph this within it. Make sure it looks the same. So remember, the mean value has to be 25, and can you tell it's much little thinner than this original graph. So let's do that. That's what you want to do. That's how I would approach it to visually. So for example, what I'm going to do is you can see that this is your mean here, and you can see, of course, it's for this here it is 32. So imagine for the new one we have is 25. So imagine drawing the 25 one. And it's going to be like that, but it's going to be much taller, as we saw. So I'm going to draw it like this, and we can see it's a little bit much more thinner, so it's going to look like this. Like that. It's going to be symmetrical. Like that. Something like this. So if I kind of rub these out, does that look nice? Yeah, that does. That looks like it's doing the job. So first of all, it's only 2 marks because you need to make sure that, of course, is the mean at 25 and is it a little bit much more thinner. Now this one's a little bit much. It's a little bit much more thinner. So I'm gonna make it a little bit much thicker because it needs to be nice like that. I have no idea, but I think that's much better. That looks much better, yeah, compared to the other one. Okay, so it's 25. Yeah, that's how this graph would look like. You don't need to label anything, so just sketch it on the same set of axes, and perfect. I hope that makes sense. Let's go. Question 5. So David is planning to build a vegetable garden in his backyard using an existing wall for one side and up to 12 meters of timber for the remaining sides. Assume that David's backyard is modeled by a flat line. David considers building a rectangle vegetable garden as shown below with the length L and the width meters. So let's understand the scenario. So basically he has this existing wall here. This existing walls, yeah? And he has 12 meters of timber for these remaining sides. So this side, and this side. Okay. That makes sense, yeah, because that's a wall. He doesn't need to put anything on the side. Okay. David uses 12 meters of timber for the remaining 3 sides. Show that the area of the rectangular vegetable garden in square meters can be expressed as this. Okay, beautiful. Now we know that the area of a rectangle is just so we know that the area of a rectangle is length times width. Isn't that correct? So for example, here our width is W and the length here is L. But what is our length though? We know that they've also given us extra information. They've told us that the timber, so you remember your timber is, so let's call it T. Timber is basically, remember your timber is, adding the 3 sides. So W, the length plus W. So basically 2W, adding those up, 2W plus length. And we know our timber is 12, so we can put 12 in there. And we can make L the subject though. So we can, if we make L the subject, it'll be 12 minus 2W. And we can sub that L into this equation. So put that W here. If L is 12 minus 2W. And expanding that, we get 12W minus 2W squared, which is what we wanted to show, the area. That's nice. Next question. Find the maximum possible area of this rectangular vegetable garden. Give your answer in square meters. Beautiful. So to find, of course, the maximum, what we need to do is, of course, we need to derive a dash of x, your area formula, and let it equal to 0. So let's go to our CAS and do that. So I'm going to press Control N here, and I'm going to define a of, it's not a of x, sorry, it's a of w. So a of w is defined as your formula for length, so which is 12w minus 2w squared. Yep. And so we want to find the maximum. So of course we can just straight away go to, we have to derive it, of course, first. So derive w in terms of a of w, and letting that equal to 0. Solve answer, comma w, which is w equals 3. Now, just basically, it can't easily make sense because you've got a negative parabola here. So if you even graphed it, it is so easy to look at. So a of x, look, the maximum. Remember, x is your width, the y-axis is your length, your area. And so you can see that the maximum area occurs, what's the x value here? Menu, analyze graph, maximum. Your x value is 3, so your width is 3, and your area is 18, just by looking at it like that. So we got the width, and so subbing it back to our area, that's where the maximum occurs. A of 18 is, A of 3, what am I doing? A of 3, subbing 3, that's where the maximum occurs, is your area is 18. That's your maximum area. Now, I also want to you can double check this also by just going menu, calculus, and function maximum of this function, so a of w, where w, of course, is width, which is something, it's positive, of course, 0 to infinity, we can say. Enter, and yeah, it still occurs at w equals 3. So let's write that down in our iPad. Let's go. So what I'm going to do is actually put w here. So what is a dash of w? We know it's 12 minus 4, w equals 0. And we learned that w equals 3, that's where the max occurs. And so your maximum, so find the maximum area of just maximum. So a of 3, it gives us 18. So your final answer is meters squared. So 18 meters squared. Really, really nice. Next question. David realizes that his new vegetable garden must fit within a boundary created by his garden path. Let the existing wall be defined by the x-axis, so this x-axis, and the boundary of the garden path defined by this continuous function g. And g is that. Okay, so yeah, it's a hybrid function. Okay, beautiful. So both x and y have units of meters. David considers a rectangular vegetable garden with 2 corners on the existing wall and 2 corners on the boundary of the garden path. Okay, makes sense. Let w meters be the width of the rectangular vegetable garden, perpendicular to the existing wall, which it is, and aw be basically square meters to be the area of that rectangle vegetable garden. Given that g is continuous, find the value of k. Okay, that's not too bad. So you can see that g is continuous over here, yeah? So, how do you, when they tell you if it is continuous, it means that basically, if you sub in the, for example, k, when we sub in k into this equation, it's going to give us the same y value as subbing k into this equation because they are continuous. Does that make sense? For example, this part of this equation, so this part over here is this equation over here, the top one, isn't it, yeah? And this part over here is this equation over here. Now, what basically is can you say they meet at the point k? So if you sub in k here, it gives you the same y value as your, as just subbing k into this here. Also gives you the same y value. So what we can do, of course, is do this. So we can basically say that when we sub in k into this, it's going to equal to subbing k into this. So we can equate them. So 3 log e x equals 2 log e 12 minus x. Now remember, x is when you sub in k, all these x's, you sub in k in here, and basically solve this. Of course, get rid of that 3 by making k to the power 3. Get rid of that 2 by 12 minus k to the power squared. Bring the squared in there. And of course, you can get rid of those logs now from both sides. And it'll be 12 minus k to the power of squared. That, and you could just use your CAS to solve that. K equals what? Just use your CAS. So let's go in our CAS and say basically solve k to the power of 3 equals 12 minus k squared, comma k. So k equals 4, which is correct, as you can see, that the k value here is a positive number. And it is actually at 4, as you can see. So they've actually drawn it really nice for us here. So perfect. So that's quite exact. So k equals 4. All right, beautiful. Might as well just use this color here. Okay, next question. Show that the area, so a of w, the same area of that rectangle is given by this formula. Now they've actually used exponential, like e's now. So, okay. So we know that the area of this rectangle, again, is what? We know that the area of a rectangle is just length times the width, yeah? Coming back to here, we know area of a triangle, so, not triangle, length times width. So we know that area of a rectangle is length times width. And can you see how they multiplied the width in there? So that's your width. So this has to represent the length. Isn't that correct? This here represents the length of our formula. Now, how do we find the length of this over here? So it's really easy because like we have these 2 points here. Can you see these 2 points? So this point here and this point here. Yeah. Let's call this point, the x value here. Let's call it x1. And let's call this x value over here x2. We know that when we sub in, for example, g into the function g of x1, when we sub in g of x1, it's going to give us the width w. It's going to give us the length w, yeah? W. Is that correct? So imagine, and remember, it's the left-hand side of this, so you have to use this one over here. So basically we're saying, hey, 3 log e of x1 is equal to w. Yeah? And you can divide both sides by 3. Yep. And then make it, x1 will become e to the power of w over 3. So that's your x1 here, basically. This value here. So if I was doing this as a coordinate, it'll be e w over 3, comma, w. That is this coordinate over here. Like that. Like that. And this one, so also the same, the way we would do it. So basically when we sub in g of w, x2, it's then also equal to w, because that's the y length. That's your y value. So, but you have to sub it into this one because it's the second part of it. So what we need to do is 2 log e 12 minus x2 equals w. So imagine divide both sides by 2. It'll be log e 12 minus x2. So e to the power of w over 2 equals 12 minus x2. So x2 will be 12 minus EW over 2. That's a lot of, ooh. Yeah, so basically what's happened here is I'm going to need to rub all this out. This is just all this extra info. You would have to show all that working out in that in this section over here, which I'm not going to do because it's going to take some time. So imagine showing all this working out here, what I'm rubbing off basically. So we get that over here. So that's your x value over here. So the x value is 12 minus EW over 2. And the y value, of course, is still w. Beautiful. So we got these two. So we got x2 and x1. And of course, the length is just minusing this here by this. So length is, of course, 12 minus EW over 2 minus your other x value, which is e to the power of w over 3. That's your length, and that's how we get this length over here. So we know we can say, hey, then area is your length, which is this whole thing, times w, which you can write just w. 12 minus e w over 2 minus e w over 3. And that's how we actually get it. So, of course, you want to show all that working out here, by the way. When we did that question, so, like, for example, all the things that are rubbed out, which is quite useful, actually, you would have put it here. I just I made sure to do it there because I wanted to show how to get those values. Make sense? Okay. Yeah. Now I might just show some stuff here actually. So for example, we said so like x1. So we said g of x1 is equal to w, and so which was like 3 log e. So 3 log e of x1 equals w, and so log e of x1 is w over 3. So hence x1 is equal to e w over 3. That's the first one, and imagine doing the same for the other one. W, which is 2 log e, what is it? 2 log e 12 minus x, so 12 minus x2 equals w, which you can say log e of 12 minus x2 w over 2, so e w over 2 equals 12 minus x2, and so x2 is equal to 12 minus e w over 2, and so that's how we get basically all that stuff. And yeah, it's not too bad, so it's really simple for 2 marks there. Okay, next question. Hence, so using that here, so using your previous answer, find the value of w that gives the maximum area of this rectangular vegetable garden and state that maximum w of AW. Give your answer correct to 2 decimal places. Okay, not too bad. So, of course, to find the maximum, of course, you have to derive A of w and let it equal to 0. And let's just do that all with our CAS. So, okay, so first of all, I'm going to make a new problem because we're going to define the new AW, of course. So, insert new problem. Okay. So, your new AW equation is our w times 12 minus so w over 2 minus, can't copy this, over 3. Just want to double check if I made any mistakes. That looks correct. Okay, so I want to find the maximum. So I want to, of course, derive it in terms of w. So A of w, let it equal to 0, of course. Solve it, comma, w. And so we get this w. Now, we're not too sure if this is your maximum area, of course. Always double check. So what I'm going to do, of course, is you can easily just graph it. Like, let's look at it by just graphing it. Oh, yeah, this is beauty. It's just it looks like a normal parabola. And this is your maximum value. Absolute beauty here. And so 2.49, 15.5. So, yep, 2.49, absolutely. So it fits everything. So let's write what we have to write down. So write your derivative. We'll write this, let it equal to 0, and just get the answer and sub it into the original equation. So our original equation is A of this here. So this is your area also. Start that down. Yeah, let's go. So 2 marks. So what I'm going to do is I'm going to write negative w over 2 minus 1 e w over 2 plus minus w over 3 minus 1 e w over 3 plus 12 equals 0. And so we found out that w, solving that, we gave us w is 2.49. To 2 decimal places, is it? Yeah, to 2 decimal, so yeah, 2.49. And the area, so subbing it, a 2.49 gave us an area of, going down, so 2 decimal place is 15.52 basically. 15.52. That is it. So, of course, in meters squared, and that's meters. Okay. That's how I would do that. Then not too bad. So, this question has already started really nicely. Nothing too spectacular. So, that's good. Next question. Can David build a rectangular vegetable garden of maximum area as described in part B? Yep, so this one. So this, you know how this is your maximum area? Can he build it with less than 12 meters of timber? So, how can we know? Well, so he's saying less than 12 meters, like 12. So, for example, we know that timber, the formula for timber was what? Going back. The timber that he has to do is, of course, remember it was this length. Sorry, it was this length plus 2w, these two here. So basically 2w plus length, basically. 2w plus length, yeah? That's your thing. Which, of course, I'll bring this timber equals timber here. Now, we're saying that we want to build it with less than 12 meters of timber. So we want this part here to be less than 12. And so you got this beautiful inequality that you can kind of bring that 2w on the other side. And so we want to, for example, does these values over here for maximum area, do they satisfy this inequality? Because if they satisfy it, then this makes sense. It's less than 12 meters of timber. We can actually build it. But if these over here, so sorry, what just happened there? If these don't satisfy, for example, W and the length, if they don't satisfy this equation, then we can't build it. And so that's what we need to do. So what we know is, of course, the width for maximum area is 2.49. Yeah, isn't that correct? So we can say the width is 2.49. But what the length? How do we know the length? Well, it's easy because remember it's just it's a normal rectangle. You remember a rectangle. So for example, if I know the width of it is like 2.49, and this is the length, I know you multiply both of them, don't you? Yeah, multiply both of them to get the area, the maximum area, which is of course 15.52. So basically, you divide this by that, and you get the length. Yeah. So your length would be equal to what? Let's go in our CAS. So it's this area, basically, it's area divided by the width. So area divided by this, the width, basically. Which gives you 6.23. This is your length. So let's write just 6.23 here. 6.23. Okay. Now we got the width and length for the maximum area. Let's sub it into this inequality and see if it works. So length is 6.23. Is it less or equal to 12 minus 2w? 2.49. Let's go on our CAS and write that down. Is this less or equal to 12 minus 2w, which is that? And it's true. It is actually. So this inequality works, which means he can actually build it. It satisfies this inequality. Yeah? This is true. So David can build it, actually. David can build it as it satisfies this inequality. Can David build this? David can build it. David can build it as it satisfies this inequality. I don't even know if I spelled it right, but yeah, this inequality. This inequality. And yeah, that's how I would kind of show that. Beautiful, 1 marker. I think you just have to write that, but yeah, using that helps you a lot. How long left? Oh, last question, actually. Okay. Finally, David considers a pentagonal vegetable garden using the existing walls from one side. So, okay. So this here side, it's the same thing. So this side here, just from the wall. And 12 meters of timber for the remaining 4 sides. Of course, now we have 4 sides. 1, 2, 3, and 4. Okay, for the remaining 4 sides. He requires 2 sides of equal length of W. Okay, makes sense. From the existing walls on the garden, G of X. Both of these sides are perpendicular to the existing wall. The remaining 2 sides will meet at this point. Okay, makes sense. The function G and the value of K are still defined from those of part B. Alright, so we've calculated already K from the last question. So this here, I'm just going to write it. Because the same, it's just basically, remember K was 4? And basically G of 4. Just running it nicely. Okay. The function G and the value of K are those defined in part B. Okay. Find the maximum possible area for this pentagonal vegetable garden that David can build with 12 meters of timber or less. Okay, so we're saying basically the timber can be less or equal to 12. Give your answer to square in square meters, Okay, so first of all, we need to find a formula for the area of this pentagonal vegetable garden, which is not too bad because you can actually just split it into 2 parts to it, can't you? You can, this here is a triangle and this is a rectangle. And this here is just the same as the original one. Like, everything's kind of the same. So, for example, this point over here is kind of, let me go back up here. So, like, these here are the same. We can take these here. I'm going to duplicate those and put them at the bottom. Okay, these are the same. They haven't changed, because it's the same equation. Okay, so we've got these 2 coordinates here. Yeah. So for example, and by the way, this area of this here, rectangle, it's really easy because we've already calculated. It's just A of W, the original here. This is the area of that rectangle. Beautiful. So we need to just find like the area of this triangle, which is not bad because we know that the area of a so let's say area of this pentagon or whatever is equal to area of your triangle plus the area of this rectangle. Isn't that correct? And we know that the area of this rectangle, so we know that the area of a rectangle is just A of W. A of W. So area of this triangle, we can calculate that. Area of a triangle, of course, is half your base. Now, what's the base though? This base, of course, was the original, like, you know, the here. You know how this is the base of it? This is the length, yeah? Isn't that the same as the base, by the way? Like, you know how this is the length, yeah? Which is basically, just looking at it, it's 12 minus E W over 2 minus E W over 3. So you minus these two, yeah? So that's going to give you the base. And the height is just basically G of 4 minus W. G of 4 minus W. So this here is overall your area of a triangle, so area of A of T. So putting that all together, your area of this pentagonal is your area of a triangle. Let's do it with a CAS now because there's so much happening here. So adding all of those up. So okay, so area of this pentagonal is, of course, we said half times 12 minus E to the power of W over 2, I'm just going to copy that actually, minus W over 3 times G of 4. Oh my god, we haven't even defined G, bro. Like, this is such a pain. Okay, that's not too bad. Wait, G of 4 minus W. Okay, so let's just write that down. We're going to define G, of course. We're going back. So G of X was what? So G of X was in this here. So going back to it, I'm going to just define. We're going to look at it back. Where was it? Okay, G of 4 is, of course, 3 ln, so natural log of X, which was from 1 less or equal to X less or equal to 4. So 4 less or equal to X less or equal to 11. And it was 2 natural log 12 minus 6. Okay, so done. We've defined it, and we can. This is your area of the triangle. Yeah, we got this area of a triangle. Remember, we're gonna add it with the area of the rectangle, which is, of course, area of W. That's your rectangle. So this is your overall area. This is the overall area of that pentagonal. Yeah, isn't that correct? So what our goal is basically is to find the maximum possible area, and to do that, of course, we can just like cover. It's really what we can do is first. Let's write this down. Actually, let's also write this down. Right, is the area, like the area of a triangle. Let's write that of that pentagonal first. So negative W plus 6 log E 2 E W over 2 plus E W over 3 minus 12. It's all over 2. Okay. Now, we know, like, for example, I'm going to call this now A of X overall. A of W, sorry. A of W. Now, of course, to find the maximum, we normally derive it and stuff. Before we do that, let's actually go on our CAS. So what we can do is just use our CAS, to be honest. Like, first of all, let's see how it looks when we graph it first. Wait, is it a basic graph first? W equals X, so make it in terms of X. All right, writing it here. Okay, so it is a parabola. Okay. So this is actually not bad. So for example, what we can do is, derive it. So we can derive it in terms of W, this whole function here. And which is going to be, of course, you derive it, which gives you, I'm not writing that down. But so imagine you derive it and you let it equal to 0 and you solve answer, comma, W. So that is where your maximum, that's your maximum width. And of course, the area is just going back to the area formula, which is this for the overall area. You put that in there to get the maximum area, which is 23.32. Now, I'm not too certain. That looks too easy, though. For 4 marks, doesn't certainly look too bad. Because we have to also meet that condition where the timber has to be less or equal to 12. So what we need to look at is we have to look at extra parts here. So let's go back to our iPad and let's look at the formula for timber. So we need to also like satisfy the timber. It has to be less or equal to 12. So for example, we know that the timber is going to be, of course, what's the formula for timber? Timber is just going to be your 2W, so these two lengths over here, plus, you know, these two over here. And to get the lengths of those, it's really easy. It's just using the square root, like the distance formula for both, yeah? So, for example, the distance for this one would be like g of w, sorry, g of 4, my apologies. G of 4 minus w squared plus 4 minus e w over 3, and you square that. So that is that, and then plus, now you also have to get the length of this, which you can say g of 4 minus w. It's kind of the same thing, so I'm just going to kind of recopy this. Most of it's the same thing. Okay, so g of 4 minus w, same thing, so g of 4 minus w, 4 minus now, but this part here, okay, but this part over here, it's 4 minus 12 minus e w over 2 all squared. Not all squared, but like outside squared. Okay, that's it. So that here will give you the length of the timber, basically, which we can kind of just do on the CAS. So let's do that. So timber is going to be basically 2w, we said, plus the square root of g of 4 minus w squared plus 4 minus e. No, one moment, just let me take that here. Yeah, 4 minus e, basically that, squared, plus, I'm going to recopy this, put that there, and so it's all the same, but it'll be 4 minus, now taking this out, it'll be 4 minus e to 12, so basically 12 minus e to the power of this, or squared. So the squared goes outside, of course. Okay, so this here is my formula for my timber, yeah? Isn't that correct? So let's think about it. All right, so this is my formula for the timber, and this is my formula for the timber, and so we want to remember the timber, the formula for the timber has to be less or equal to 12, yeah? Because the timber, yeah, has to be less or equal to 12. Now, does this here, so let me copy this, does the width, you know, for when we calculate the maximum area, fit it? You know how this is the width we got? Does it fit, does it satisfy the timber ratio? False, it actually doesn't. This is where they trick you guys. Do not fall into that trap. They are tricking you here. This is what I mean. It sounded too easy for those 4 marks. So how do we think about it? Okay, well, one of the best ways what I'll do is like think about it is I'll take this timber equation, yeah? And I'll look at the values that satisfies the timber to work. Like for example, I'll take this and I'll make sure I'll write it in terms of x so I can graph it. I'll take this whole thing and I'll graph it. Enter. Control, and let me zoom out. Zoom here. Okay, so this is the graph, yeah? You see this graph here? Okay, so remember the timber, draw y equals 12, so that to show where the timber has to be. Okay, remember they say the timber has to be less or equal to 12, so it can be equal to 12, which is only occurring at here. So this is the y equals 12, so we're only looking at this part over here, And you can see that, for example, the timber is equal to 12 here, and the timber is also equal to 12 at this point over here. Now, remember, the more you use the timber, the more likely you're going to have a large area. So we got 2 points here, yeah? You got this point here, which has a high width, and this one has a small width. Let's find those widths first. So, for example, it's just basically taking this here. No, let's take the original, actually. Let's take the original. And let it equal to 12, and solve for w. And so comma w. And this is giving me the widths, yeah? We only care about those two positives, yeah? For example, these two widths here, this here and this here, we're going to check which which one would likely give us the largest area, which is easy because we have the area formula. Can we just sub it in there? Let's just sub them in there. I'll take this. I'll sub in the first one, this one here. So sub that in it. Okay, we got 19.88. Let's sub it in the next one, which is this over here. Negative area absolutely doesn't work. So guess what? This one over here, this largest width is actually rubbish. It's this one that actually is perfect because it gives you a really large and it's within this where the timber is less or equal to 12. Let's check these values over here. What happens if you start to increase? Do you see how you start to increase that width here? What about, like, for example, this point over here? This point looks very cool. I would, so for example, I'll go to geometry just to look at that point. specifically point on. So it's like 4.15. So if I did like 4.15 here, 4.15. Yeah, so the area is small. The area is becoming small. So, for example, when we put like that 2, this is where the maximum area is. So if we increase it, let's say at 2.8. So as we go more to the right, it's the area is actually decreasing. So that's not good. So basically this here looks like this is where the maximum area occurs. This point over here. Does that make sense? So be careful. This is where the actual real, because it both satisfies that the timber is less or equal to 12 and also is the large area. So we want to write basically this over here. This is your width and this is the area, the maximum possible area basically. Okay, so your width is so 2.63831, yeah? And so subbing it into A of W gives you 19 point, how many decimal places? 2 decimal places. 19.88 meters squared. Beautiful. That's all they went. Find the maximum possible area for the pentagon. Give you answer. Okay, beautiful. That is it. All right, that actually makes more sense. Yeah, be careful, especially it's the last question. It's supposed to be hard. So yeah, I hope this video helps you in understanding how to do this. Again, these are just suggested solutions. Take them with caution. But yeah, thank you guys for watching, and please make sure to like and subscribe, and hopefully I'll make more future videos. Take care of yourself, guys. Bye-bye.